Hi guys, start at topic 4. This is it, the home stretch. So we're going to start from the 27th of April, and it's going to take us, ignore what's written in the boxes, because obviously that was if I was going to be at school. But it's going to take us through for the next 2 weeks. The Friday is a bank holiday, halfway through to the Wednesday, and then Wednesday the 13th of May, you're going to hop over and start B2. So here's the layout of what we're about to do. I've already started drafting it all out. That should be down there. It's going to be over 8 lessons. It would have been more, like in bits, but I'm chunking it up into 8. So we're going to start off with atomic structure, ions and isotopes. We're then going to do radioactivity. Lesson 3 will be nuclear equations. You're going to look really clever when you can do those. Lesson 4 is going to be half-life of radioactive isotopes. Lesson 5 is all about the dangers of radioactivity. Lesson 6 is about the uses of it, and you'll be surprised where it is. There's some in your house. Lesson 7 will be about nuclear fusion and nuclear fission, so atomic bombs and the future of our energy. And Lesson 8, the atomic model, which you've kind of already done, but I'll be putting a physics twist on it. So, without further ado, let's start with the atomic structure. And we'll go over to an atom builder. So when the universe started out, everything was either hydrogen, which you can see here, or if we were to build the next part atom, here we go, helium. And that was it. It was in a ratio of 75% hydrogen, 25% helium, and that was it. And it wasn't until the first stars came along that we started building the periodic table. Here we have lithium. And you'll notice I'm having to balance the electrons out. So this is lithium. It's got an atomic mass at the top there of 7, and that's 3 protons, 4 neutrons, and then to balance it out electrically, for every proton I've added an electron. And so that's how we build the periodic table. We just go up 1 proton, turns it into something new. We balance out the number of, let me get that right, we balance out the number of electrons to turn it into an electrically stable not radioactive, I'm seeing it up there. Let me get the right number of beryllium. I think I've added too many. There we go. We'll talk about this radioactivity in a minute. Come on, where are you? I'm putting them in the wrong place. There we go. No. Back to lithium. All right, it blew up. Anyhow, so when we're writing out, and you've done this before in chemistry, so let's get this home. We'll start with ions and isotopes. We'll say, we'll start with a diagram of the structure of an atom. So we have this area that we call the nucleus. And this, you guys, I guarantee know all of this. This is where chemistry and physics overlap. So in the centre of a nucleus, we have the protons. I always think of them as red. They don't have colour, of course, but I think of positive as red. So we have that. And then usually roughly equally balanced, not always, we have the neutrons. And the neutrons are there to hold the atom together. So the neutrons, they were the last of the 3 particle speeds discovered because they have no charge. So we have our protons on our neutrons. And then, as Mr. Dolan's already taught you, round the outside we have orbiting. Let's get this right, put it central there, and we're going to choose a chunky white. I'm going to turn it into a dotted line. We have the first of the shells, and it was Niels Bohr who gave us this idea that electrons exist in shells. I usually draw electrons blue, but given that the neutrons have got it, I'm going to go with green. So we have in orbits, electrons orbiting. And we have 1, 2, 3, 4, 5, 6. So in this case, we're going to have, now let me see if I can cheat and do this. I'm going to have 6 electrons. So I'm going to paste that, I'm going to make that bigger, and I'm going to place it around there. Just need to draw in my dotted lines. I'll do. There we go. Now, there's often a bit of banter between chemists and physicists We always joke that we're the ones who discovered the protons and neutrons. We understand the electrons, and without that, you wouldn't have chemistry. And if you're a chemist, your life is going to be all about the electrons. They form chemistry. But with physics, we go into the nucleus. We look at how we can split that and how atoms are actually formed. So we've got the nucleus, we've got 2 there, we need 4 more. So we're going to go 1, let's keep it right, let's do them as dots. 1, 2, 3, 4. And in this case, 1, 2, 3, 4, 5, 6. Yeah, in this case, we've got something quite familiar to us all. Hopefully by now you've realised we've got here a carbon atom. I did not know I was going to draw a carbon atom. I just randomly did dots. Worked out well. And you've obviously seen for years that we write the first letter, sometimes the second letter too, for the symbol. Also, wrong button. Linking in, we have a number at the top, which is called the atomic mass. Atomic mass. And at the bottom, and this one's got a couple of numbers, it's sometimes called the atomic number or the proton number. And scientists hop between the two, so don't worry too much about fixating on it if somebody says something different. So in this case, we've got 12 in the middle. Let's just check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yep. And that's the mass. It's the total number of protons and neutrons. And then in the atomic number, we've got 6. And it's the 6 that means it's carbon. If it was 5 or if it was 7, it wouldn't be carbon anymore. So protons make it the thing that it is. Hopefully by now I've not taught you anything you don't already know. Right, now we get on to ions. We'll start with that first. And again, hopefully you know what this is. So ions are where you have an imbalance of electrons. All atoms want to be electrically stable. Let's take a proton away, let it blow up a few times. Take off the neutrons. They're tricky to catch. Right, here we go. Let it blow up a few more times. Sort itself out. We'll look at why it does this in a few lessons' time. Can we just cheat and go straight back to... There we go. Let's try lithium with 3. Okay. Can I get rid of the words? Yes, I can. Okay. 3 protons. So around the outside there, we've got 3 electrons. I think... There we go. We have 2 in the first shell, 1 in the second. If, however, I get it to hold on to another electron, we're going to have 2 and 2. And I blew it up. So when we have an imbalance of electrons, either we have too many, and here I have a 4- ion, or we take them away and we have too few. It's really hard to make them stick. You have to be slow. There we go. Now we start taking them away. Oh, it's going to blow again. There we go. You create an ion. So we'll write that down. Ions are atoms with an imbalance of electrons. And that's the whole principle of ionic bonding. So you've all done about how chlorine group 7 bonds to sodium group 1 because they exchange electrons to have full shells, creates ions, plus ion sodium, negative ion chlorine, and that causes them to bond together. So it's exactly the same thing. So imbalance of electrons. The bit I want to focus on though, you may or may not have done, is isotopes. You may have noticed when you look at the periodic table, I don't know if this one I've got here has got the picture on it. I've got the right one. No, it's simplified. But when you've looked at the periodic table and the teacher explains that the number at the top is the mass and the number at the bottom is the atomic number, you might wonder how the hell they manage a fraction. For example, chlorine, if I remember correctly, they quote a mass of 37.5. So the smarter kids in the group start thinking, have I got half a neutron, half a proton? Is that a thing? And I love it when kids mention that and they notice it. And it's not. It's all to do with the abundance. Because an isotope is an atom with an imbalance of neutrons. So just like we can add and subtract electrons, we can also have in nature an imbalance of neutrons too. And it can either happen naturally or we can now force it and create all sorts of amazing things. So when we take chlorine as an example, chlorine has two main isotopes. 25% of chlorine, I'm going to go from memory here and I'm getting it wrong, is 36, let me look it up. Isotopes of chlorine. I'm rusty. Isotopes. I've spelled isotopes wrong as well. Of chlorine. 35 and 37. So it's 35.5. It's coming back to me now. 75. There we go. So it's 35.5. There we go. So we have 75% of all chlorines are a relative atomic mass of 35, but 25%, 1 in 4, are a relative atomic mass of 37. And so in that box, when they're showing the relative atomic mass in a periodic table, what they're actually showing you is the percentage distribution of that mass. So if it's like if it was, I don't know, 37.1, it means probably there's loads of 37s, probably 90%, and then maybe 10% is 38. And so they take the weighted average of those. And we can see it in action. This is one of my favourite small apps. Let's hope it's still installed. It's called Nucleotide. And what you're looking at here, it takes a while to process what you're actually seeing. But you're seeing along here in ascending order going up is adding on a proton. So you've got the classic periodic table. And it starts here, 1, 1. If we go 1 across, we get to the isotope 2, 1. This is called deuterium, du meaning 2. This is called tritium, tri, 3 masses in the middle, 2 protons, 1 neutron. There is a very rare lived element isotope with 4 and 5. However, these exist for such a minuscule amount of time as to be insignificant. We then move across, we're on the diagonal. So if we go across the diagonal, we reach the stable element of helium, 4,2. However, it has an isotope, 3,2. And so across here, we have all the isotopes. Lithium, 7,3 is the stable one, so that's the one you'll see on a periodic table. Beryllium, and we move along the diagonals. And this is called the zone of stability. You'll notice they're pink. So if we take, for example, there is the most abundant version of oxygen. However, there are isotopes of it. Abundance of this type of isotope, 0.2%. This one, 0.038%. Yeah, if we choose the main one, 99.757%. So what you see on the periodic table is kind of the most popular, stable version of that atom. And all the other ones are isotopes of that atom. And some have lots of isotopes. Most of them are very short-lived. You'll notice the colours are grouping, and the less short-lived are over here, the yellows, the whites. They go almost instantly. And this zone of stability carries on up through. Bit of a break here. The zone moves right across. Loads of gallium, loads of krypton. But then something special happens. It stops. but the periodic table carries on. And it stops because the atoms can't get themselves into a stable configuration anymore. Around lead, around bismuth, you start getting unstable elements. And these are the ones at the bottom of the periodic table that have those radioactive symbols next to them. And it's the fact that they can't form stable atoms that causes them to decay. And again, we'll talk about this more in the future. So, final thing we can say on this, we'll give the example of hydrogen. So, we'll do an e.g. hydrogen. So, standard hydrogen is H11, one proton. We're not going to bother about the electrons on this. Then we have an isotope called called deuterium, which is one proton and one neutron. So we call it H21. And chemically, it's identical. It forms water. It explodes with fire. However, it weighs twice as much. So sometimes you hear this phrase heavy water. They use it in the nuclear industry. And it's when they create this deuterium and bond it with oxygen to create heavy water. And it's better at absorbing radioactivity. And then the third one is tritium. And again, chemically identical, forms heavy water. So this time we have a proton, a neutron, and another neutron. There we go. So that's an example. There'll be some questions attached and probably a link. I haven't quite planned it out yet. But any questions, as always, email me or in the comments section. Cheers. Bye.